coders, and welcome to Code Disclosed. In this video, I will explain the algorithm of the bisection method, and I will implement it on an example using MATLAB later on. So let's start first with explaining what the bisection method is. The bisection method, or also known as the interval halving method, is an iterative algorithm and a powerful numerical technique that provides a systematic approach to finding the root of a continuous function f of x which is defined within an interval a, b. To bisect something means to cut it in half, and that is the root of or the essence of this method. The bisection method searches for a solution by bisecting, which means narrowing down the search area by half at each step. All right, just a refresh of memory. If for a given function f of x, the process of finding the root involves finding x0, the point x0 where our function equals 0. So once we find this point, then we've found our root. Okay. Now let's go through the algorithm of this method step by step, and let's take an example. This function, which is f of x equals x cubed plus 1. Now, very first step in this method is to locate or define 2 points. The first one is on the left of the interval, and the second one is on the right of the interval. So you have xl, x left, and xr, x right. So your interval, your function is defined within this interval, xl, xr. The second step is to calculate the half point of this interval, which is xc. So xc here is xr plus xl over 2. Here you have two regions now. You have the left region and the left region on the left of the middle point, and the right region on the right of the middle point. The next step is to calculate or to evaluate our function at this middle point and see where this function lies. So in this case here, if we evaluate at xc, you can find that our fxc is positive. Now, if this is the case, if fxc is positive, then our root is definitely lies in this area here, in the left region. For this case, we need to shift or move the right boundary and put it equal to the middle point. Now, let's do exactly the same thing. Let's half it. Let's half our new interval and calculate xc. And now we have two regions here. We have left on the left of the middle point and right on the right of the middle point. Let's calculate our function, and we can see here that when we calculate our function at xc, our function becomes negative. This means that the root is definitely on the right region now. For this case, we need to move the left boundary we have and put it equal to the middle point. Okay, let's do that again. Let's half it, and then we have two regions, and then we need to evaluate our function at xc. You can see here that our function is still above 0 and still negative, which means that our root lies on the left now. Let's do exactly the same and move the right boundary and put it equal to the middle point, and let's half it. And let's evaluate the function at the half, and then you can see here that our function lies very close to 0, which means that the middle point here is our root. That's the root that we are searching for. Okay, now the question is how we can code this. All right, to answer this question, let's go to MATLAB. Now let's start our code as usual. Let's start our code with clear all to clear all previously assigned variables, and close all to close all previously opened figures or plots. And then let's put CLC to clear your command window, and this will declutter the code screen that you have. All right. Now the first step, let's define the x x-axis. So x here is line space. I'm gonna make it go from -10 to 10 with 100 points. All right, now this is the x-axis. Let's define our function. So let's define the function. And f here, I'm gonna use exactly the same function that we used in the explanation PowerPoint. So x3 plus 1. And you can see here that I have to put this dot here because x is a vector in this case, not a point. Let's plot it and see how it looks like. So let's go for a figure. Let's construct a figure and let's plot x, f, and let's plot it in blue. And then let's go for a line width of 1.5. We need to define the x label, and we need to define the y label, which is y, and let's add a title for this as well. In this case it's x, so it's f equals x cubed plus 1. All right, maybe let's define as well the y limit of the figure. I want it to go from -10 to 10, and I want the x limit to go from -3 to 3. Hopefully no complaints. Let's run this and see how it goes. All right, good. So this is the figure that we have, x, y, and this is our function, which is x cubed plus 1. Good. Now let's find the root of this function. Now we need to implement the bisection method. Now, as we have seen before, the very first step in this algorithm is to define the interval. So I need to define the x left, which is in our case, I'll consider it's 3, for example. So this is the left boundary. And I need to define x right, which is, I'm gonna say it's 2, for example. So this is the right boundary. Okay, now I need to do the iterations now. I need to go through through these points, half the intervals, keep halving until the value of the f is equal to 0. So let's go for iter, which is the iteration. I want it to go from 1, let's say 1,000, because I don't know how many iterations it would take. So this is the number of the iterations. Okay, now second step, I need to calculate the half of the interval of xr and x left. So I need xc, which is x left plus xr over 2. So this is the middle point of the interval. Okay, now I need to calculate my function at that point. So c now is xc cubed plus 1. And you can see here that I didn't put the dot as before, because before I used x as a vector, but here x is just a point, which is the middle point. So this is the value of the function at the middle point. Okay, now I need to use an if statement. I need to say if this function is positive, larger than 0, then move the right boundary and put it equals to the middle point. So move the right boundary here. Else, all the other cases, okay, move the left and put it equals to xc. So this is move the left boundary in this case. All right, let's end the if statement here. There is another if statement. If the absolute value of my fc, of my function, is less than 10 to the power of -5, which is very close to 0. So if the value of my function is near 0, then break the iteration, because I have reached the root, basically. And let's end this, and let's end the for loop as well. Okay, I think this is the algorithm, but I want to print the number of the total iterations that the algorithm takes until it reaches the root, which is iter. I want to print the root as well, which is xc in my case. I want to print the value of the function, which is fc. I want to make sure that it equals to 0. All right, let's run this and see what the root would be and what fc is. Okay, so fc here is very close to 0, is to the power of -6, so it's 0 basically. The xc here, which is the root, is -1, so let's locate the -1 on the figure. It's right there, somewhere here. So this is -1, and this is the value of the y, or the function, which is 0. And the bisection method took 19 iterations to reach this root. All right, so this is it for the bisection method, and this is how you code it using MATLAB for a given function x cubed plus 1. You can find this code in the GitHub link in the description below. If you have another method or another way to code this, please do let me know. And thank you very much.